Yeah, so I will pass things over to Steve, who is the senior cloud engineer at QuestDB, and he's going to be talking about day two operations with Kubebuilder.
Thank you for the introduction. Can everyone, or can you see my screen?
Yep.
Awesome. Okay. Of course, you have to start with that. So, I'm here today to talk about automating day two operations with Kubebuilder and Operator SDK. Um, First, just a little bit about myself to give you a brief background. I started my career on Wall Street. So I guess you could actually say that my first programming language was Excel VBA, which is a little divisive, but I personally consider that to be a programming language. I've basically worked on Wall Street, building software for hedge funds and investment banks, and moved into the startup realm a while ago. I currently work for QuestDB. We are building a high-performance time series database with a focus on ease of usability and also, again, with the high performance. You can ingest up to millions of rows per second if you want to and have that type of data. You can query extremely efficiently as well. And everything is, or at least on the querying side, is done through SQL, which personally I enjoy a lot. But here today, here to talk about Kubernetes operators. And sorry about that. Here to talk about Kubernetes operators and what they are and how we can use them to automate day two operations. So first, I'm just going to go into a brief introduction about what operators are. If you read the snippet from the Kubernetes docs, it's a little vague and not entirely clear what an operator is. Talks about these things called custom resources that are used to manage applications and their components. It's very vague, and personally, when I was reading that, I had a hard time understanding why I would ever need an operator. But we do know that there are hundreds of operators out there available for you to download. Almost every major software vendor and package, when you deploy it into your Kubernetes cluster, is also includes an operator. So we know that they're important and they're a growing part of the ecosystem. So I like to think of operators as pieces of code that you can deploy inside of your cluster that are used to automate the things that you would traditionally do as a DevOps engineer or a cluster admin. Things like hooking together applications, writing YAML, debugging or fixing issues that arise. These are all things that operators are designed to potentially automate so that you can run an operator inside your cluster and you don't necessarily have to perform all of these manual actions. But to really understand what operators are, I think it's important to go into a little bit about custom resources and custom resource definitions. So a custom resource definition is a specification of a new type of Kubernetes object that you create and that you can deploy into your cluster and then use. So I like to think of a custom resource definition as kind of a class definition of a new type of Kubernetes object. And a custom resource is the implementation of that class. So an operator will consist of one or more custom resource definitions and will have its own set of API groups that you can then use to reference and create your various custom resources based off of. Custom resource definitions themselves are actually Kubernetes resources, and you can interact with them in the same way that you can in any other Kubernetes resource. So here I get them. You can update them, delete them, and interact with them in any way that you normally would any other normal Kubernetes resource. There are two main components to custom resource definitions and custom resources, and really just any Kubernetes resource in general. You have its spec and its status. The object's spec represents its desired state. And when we are dealing with YAML manifests and applying them and working with all of the tools that work with these manifests, we are dealing with objects' specs and their desired state. This is generally controlled either by us, the end user, or internal cluster components as well. For example, if you create a deployment, the deployment controller will modify the spec of the replica set that's underlying the deployment. On the other hand, we have status. Status reflects the actual state of your object and the cluster. These things are not these things are updated by the in-cluster components such as controllers or other pieces that are running inside of the Kubernetes control plane. So I've kind of brought up a lot of terminology, and I want to just clarify it because it can get a little confusing. Starting from the bottom and working our way up, we have custom resource definitions, which are, as I mentioned, these schemas of custom new types of resources that you can deploy into your clusters, like a new class in Java. You then have custom resources, which are implementation or instances of that class. So when you create a custom resource, it's based off of a blueprint of a custom resource definition. Any changes to custom resources, creations, modifications, or deletions are picked up by reconciler loops. And these loops are running inside of controllers. Controllers, you generally have one controller per custom resource definition, and I'll go into that a little bit later. Controllers are pieces of code that are running in a pod along with admission webhooks. These webhooks are used for validating API calls so that you can prevent your custom resource from entering some kind of invalid state, as well as defaulting webhooks so that when you initially create an object, you can set some defaults. Controllers and admission webhooks are running inside of a manager. And that manager is running in a pod in your cluster, generally as part of a deployment to take advantage of all of the wonderful things that deployments give us, such as easy upgrades and rolling upgrades, and also high availability if you choose to do so. So I generally consider an operator to be the sum of your manager YAML manifests, as well as your custom resource definition manifests. So I hope that gave you a little introduction about what operators are in the Kubernetes ecosystem. And now I'm going to talk about day two operations and why we would want to automate them. So the typical software lifecycle starts at day zero, where we have nothing, a blank whiteboard, a blank project file. We are spending the time to design our solution, maybe gather requirements if we're lucky, architect our solution, write code, create CI/CD pipelines, figure out how we're actually going to deploy it. And once we've deployed our application, we've hit day one. But as we all know, it doesn't really just end there. In fact, it only begins. All the things that are required to keep your application running, especially at a production level, are considered to be day two operations. I took this chart from the Operator SDK docs, and I think it's a really good demonstration of where day one ends, or at least where I consider day one to end and day two to begin. The Operator SDK has a set of levels or automation levels for a particular operator and the pieces that it can automate, starting from one, which is a basic installation, and going to level 5, which is autopilot. So I would consider day one operations to be level 1, where you can configure and deploy your application. But everything else, including upgrading your application, ideally, hopefully seamlessly, the full life cycle, including backups and recovery and restores, all customized alerting and combining all of those into some really cool autopilot stuff, which is kind of everyone's goal, I would think. These are all kind of day two operations. As someone who works for QuestDB, I'm shirt here, we have a SaaS platform that I work on every day. And these are some of the day two operations that I think about. things like backing up and restoring databases and performing infrastructure upgrades of cluster components, as well as installed pieces of software inside our cluster that help everything run. Upgrading the database version itself and making sure that that process goes smoothly. Everything that observability encompasses, including monitoring metrics, telemetry, alerting. These are all things that are critical for a production service and something that I would consider to be a day two operation. Failure recovery and how we recover from failures is a critical part of that as well. I think about data migrations in terms of how to cheaply, both from a time perspective as well as a cost perspective, move data in and out of our clusters to make it easy for customers to use our service. And more recently, we introduced replication into our cloud, and that has created an entire new class of day two operations that we need to manage as well. So I'm really going to speak today about one day two operation and use this as an example to show how we can build, or rather design, a custom resource definition. Spoiler, there's actually more than one. How we can do that and design our operator to automate this one thing. And hopefully this can give you an idea of how to apply these practices to your own issues. So, and we're going to take a look at the QuestDb snapshot process, which is fairly straightforward, but does require a little bit of synchronization. You first need to run the snapshot prepare SQL command against the database. And this will basically prepare the file system for you to take a snapshot by having the database engine acquire reader locks on tables and create metadata inside of your database directory. Once the snapshot prepare command has been run, you can then actually take your snapshot. And we're not prescriptive in how you do this. For example, as long as you make a copy of your database directory, optionally, if you want to compress it and store it somewhere safe that you can restore it later, you've taken your snapshot. So you can use your favorite file system or volume manager to manage your snapshots. But it's important to run the snapshot complete SQL command once the snapshot has been taken. This will release all of the locks on the tables, or reader locks on the tables, not writer locks, just to be clear. And also, it will clean up some of the metadata and allow you to use the database as normal. So I'm going to talk now about how we can design a set of CRDs, or custom resource definitions, to model this problem. Taking a look first at a few principles that I've kind of learned over the past couple of years. So many of these I actually learned directly from the Data on Kubernetes Slack channel as I was beginning my operator journey and had a lot of questions. People here were very helpful in answering them, and I really learned a lot that way. But really, what these boil down to are simplicity. You want to keep your operator as simple as possible. And the way to do that is, in my opinion, to have a custom resource definition, or CRD, have one thing and do that thing very well. That makes your actual operator code simpler, and it makes it easier for you to reuse that CRD, which in my opinion really shows how the Kubernetes ecosystem has grown more recently, because now we're working on a base set of core resources that we can then build larger and higher level abstractions on top of. Another piece that's important is you want to keep one CRD per controller. I experimented with this a little early on and found that, kind of by trial and error, the reason for this. Basically, if you have multiple controllers that are trying to work on one custom resource, they can become in conflict, where you have one controller makes a change on the object, and then the other controller needs to get the updated version of the object from the API server before it can make its change. And then when it makes its change, your first controller is now working with a stale version of the object. So you can see that there's a conflict that will eventually get resolved, but it slows down your process significantly. If you try to reconcile multiple custom resource definitions per controller, I've found that what happens is, let's say you encounter some kind of an error and you need to exit your reconciliation loop. Let's say this happens before you're able to actually reconcile a second or third custom resource definition. Then in that case, these objects never get reconciled and they get stuck. So generally, it's best to have one custom resource definition per controller. As well as abiding by all the semantic versioning and Kubernetes API guidelines that we all follow, so that users of your operator know what it means when you actually update your API version. So given these best principles, I now have 3 custom resource definitions that I want to create. The first is a QuestDB custom resource, and this is designed to manage a single QuestDB deployment. The deployment consists of a stateful set for the runtime, persistent volume claim for storage, a service for networking, and config map. And these resources are all managed and provisioned by a single YAML manifest for a QuestDB custom resource. The next custom resource definition is a QuestDB snapshot, and this is used to manage the QuestDB snapshot process that I mentioned earlier. It orchestrates the pre and post snapshot jobs, which I've modeled with Kubernetes jobs, and also a volume snapshot, which in itself is a custom resource that comes with a variety of CSI storage drivers. So this will allow you, since I mentioned we're not really prescriptive on how you take that snapshot, you can use whatever driver and whatever storage mechanism that you use in your cluster to actually take the snapshot, and the QuestDB snapshot custom resource definition will be able to work with that. And this is a really good, I think, demonstration of the composability of various custom resources and how you can use them to build larger and more powerful abstractions. Another example of this is in the third custom resource definition that I'm going to create, which is a snapshot schedule. This way we can control the snapshots purely in Kubernetes. And I think that this is important because each QuestDB snapshot custom resource represents one snapshot. So we need a way to orchestrate multiple ones. And we can do this with the QuestDB snapshot schedule. So now I'm going to go into a little detail into each of the custom resource definitions, just to talk about what they look like and hopefully give you an understanding of why we've separated them in the way that we have. The QuestDB spec is fairly straightforward. At the end of the day, all you need to do is really specify which image or version of QuestDB you want to run and how you want to provision your storage using the volume spec. The volume spec actually provides a variety of options for you to provision. You can use a dynamic persistent volume claim by filling in the size and optionally storage class name. You can use an existing persistent volume claim by using the selector or volume name directly. And you can even restore a QuestDB directly through the spec by providing the name of a snapshot. The config spec just abstracts over the 2 common files that we use to configure QuestDB. We call them server.conf and log.conf. There are also a variety of other options that are included in the custom resource spec but are not required. And these are similar to Helm charts values, where you have the ability to customize your chart or object to your own specific environment. You can do that here as well. So for example, if we have a set of resources or resource requirements that we need, I don't know what they are, but you can fill that out directly if you need to. Same thing with node selectors, image pull secrets for private registries, and all of these things can be customized in the YAML manifest directly. So here's an example of a QuestDB. It's a pretty small spec. We actually just have the image and the volume size. So this means that we will be creating a dynamic persistent volume claim using the cluster's default storage class. That's 100 gigs. And when we kubectl apply this, we end up with an entire QuestDB deployment, including the stateful set, persistent volume claim, everything automatically created, running, hooked up, and ready to go, all based on this two field spec, which I think really shows the power of operators in that you can take a lot of these implementation details and hide them behind a simpler, more high level spec for you to use. Next, taking a look at the QuestDB snapshot. The snapshot spec takes the name of a QuestDB. In this case, it will reference a custom resource, a QuestDB custom resource. And you can also specify the volume snapshot class name, which is similar to a storage class, just defines how you are going to take your snapshots using your particular CSI driver, and a job backoff limit in case any of the jobs fail, we don't keep on trying them forever. We have one piece of status, which is the snapshot phase. And the phase directly corresponds to the different pieces of the snapshot process. So when we run the pre-snapshot job or snapshot prepare, I consider that to be the pending phase. When we're running the actual snapshot and the volume snapshot CRD is created and being used, and that controller is taking the snapshot, that would be considered the running phase. And when you run your post-snapshot job, that would be finalizing. And if any of those fail, we attempt to finalize the snapshot and then move to a failed phase. And ideally, if everything succeeds, we end up in a succeeded phase, and the snapshot custom resource, snapshot custom resource will generally have a static phase from that point on. So here's an example of a spec using the cluster's default volume snapshot class. You just have the name of the previous QuestDB that we created. We kubectl apply, and we have the synchronization of the pre-snapshot job, volume snapshot being created and run, and the post-snapshot job all happening under the hood from a one field config. So I think this custom resource demonstrates how you can use operators not just to abstract away kind of larger YAML manifests, but you can also use it for synchronization and orchestration of your various components. So finally, we have the QuestDB snapshot schedule. This spec embeds the previous spec of the QuestDB snapshot in the same way that you have kind of a pod template for a deployment. It makes it very easy to actually construct this, as I will demonstrate later. We also have a schedule, which is just a cron schedule, and for now, a fairly simple retention policy that just stores a number of successful snapshots and removes any older ones. We have some phase here to keep track of where we are in the most current snapshot and if it's time to actually take a new snapshot. So here we have a spec with a schedule in cron, a retention period, and also just the name of the QuestDB, which is basically the snapshot spec that I showed in the previous example. We kubectl apply this, and we have a series of QuestDB snapshots that are being created with their underlying volume snapshots and a bunch of jobs that have been succeeded, that are succeeded as well. So I know I took a little deep dive into custom resource definitions, but I really think it's critical in terms of constructing operators and automating your day two operations. For you to, if you sit down and kind of like think about the abstractions that you need to make and what you want to do at a high level, and also think about some of the best practices that I mentioned earlier, like keeping things simple with a single responsibility, you can actually make the process of writing your operator much more enjoyable. I know this firsthand since some of my early designs were not quite like this, and writing the operator at first seemed okay, but then I just ran into a lot of strange errors that kind of just went away after I refactored a couple times. So now I'm going to talk about how we actually build operators. And I'm going to focus, as the title, I guess, suggests, if you're familiar with these libraries, focus on Go. You can also write operators in really any language that you want. You can write them in Java, you can write them in Python, in Rust. And really, since you're communicating with the Kubernetes API over REST HTTP, as long as your programming language supports REST HTTP, you can make an operator in it. Some languages have better tooling than others, and that's the reason why I chose Go is because of the Kubebuilder framework, which is an extremely powerful scaffolding framework to that basically allows you to when you create a new project, it does a lot of the plumbing work for you. It also has a plugin system. So Operator SDK is actually a plugin of Kubebuilder that provides some additional functionality around releasing and deploying your operators. So to create a new project, you create a new Go module, you run an init command. It's going to either be operator SDK, which I used, or Kubebuilder. The commands are the same. Operator SDK just wraps it. Um, and then you run create API for each of your custom resource definitions and optionally a webhook if you need that. This is only part of it, but an entire file system is created for you, including YAML manifests, Go modules, a Docker file, make file, a README, and all of these things have to-dos for you to fill in your own custom logic. But if you run this thing, it will work. I won't do anything, but it'll work. And the YAML, one of the really powerful things and why I like writing operators in Go is the YAML auto generation features in Kubebuilder are extremely powerful. So the previous custom resources that I talked about, they looked like Go structs because they actually are Go structs. I didn't have these annotations here, but these are used by Kubebuilder and the makefile to generate custom resource definition YAML manifests, which can be fairly verbose based on your Go structs in your project. So you define your operator's API by using Go structs in a package. You can also further customize those structs by using special comments known as markers. These things you can, for example, create a what they call short name, so I don't have to type QuestDb snapshot schedule every time. I can just use a friendly acronym. You can also customize the output when you kubectl get your object. And also, since remember your controller is running in a manager and your manager is running in a pod in the cluster, but you're also operating on various other Kubernetes resources, you need RBAC and permissions to be able to manage those. And you can control your RBAC in code as well using these comments, which I find much more useful than trying to like think about the matrix of various custom resources and resources and permissions that you would normally do when editing RBAC manifests. All you need to do is run make generate manifests, and everything is created for you, including your manager code, all your controllers and webhooks. Sorry, your YAML manifests, not your code. And then also your custom resource definition YAML manifests as well are all created. And to install them, I don't have a slide for it, but you just type make install. It's very easy. So what actually goes on inside of a manager? A manager is listening to the Kubernetes API and is registered to listen to changes in various resources through a series of webhooks. In Go, this is called informers. And basically, if there is a creation, modification, or deletion of a watched resource type, that will trigger a reconciliation request for a particular custom resource. That reconciliation request will get added to a queue that's running inside your manager and eventually will be popped off by a reconciler, which is a function that processes the reconcile request. Going back to the watches, there are various different ways that you can set up these watches, and you can do that in your operator with common Kubernetes libraries. but there are a few different types of watches in Kubebuilder. The first is for, which is for the resource that your controller is actually reconciling. So if we're writing the QuestDB controller and there's a change in any QuestDB, we will be notified about that, and the name and namespace of that QuestDB will be used to create a reconcile request. Owns, which is another type of watch for the objects that our custom resource, or that our controller is actually controlling. So these are the things that we are orchestrating, like the QuestDB stateful set and config map and persistent volume claim. If there is a change in any of these resources that is owned by a QuestDB custom resource, that QuestDB custom resource will also be eligible for a re-reconciliation. These ownership these relationships are created directly in code and are actually API calls to your Kubernetes API server. So not only will this help while reconciling your various objects, but it also helps in garbage collection, since once your custom resource is deleted, all of its child resources are deleted as well. And then we have watches. So watches are basically used for any external resources that you're not managing, but you would still like to be notified about changes. So in this case, let's say we can watch like a node or a secret that we use maybe to generate our config map. We don't necessarily need to control that, but we do need to be able to map that to a particular QuestDB, generally through a label or an annotation, so that whenever there is a change in one of these objects, we know which QuestDB we need to reconcile. Inside the reconciler itself, since a reconciliation request is just a name and a namespace, the first thing we have to do is actually get the object from the API server. We then run through generally each of its control objects or each of its owned objects and run through this kind of pseudocode where we generate the desired object based on the custom resource spec. And then we get the state of that actual object from the API server. If the actual object does not exist, then we create it. And if the actual object does not match what the desired object is, then we change what we need to and update it accordingly. When we're dealing with snapshots and things like orchestration, orchestrating various components, it can get a little trickier. In this case, I have a set of handlers. This is more of a status-based approach where we basically have created somewhat of a state machine, a simple, very simple one, as I mentioned. Simplicity is key here, where we are able to migrate from one phase to the next through idempotent handler functions. And this is all very well tested, which I'll show in a second. But we all have a choice. When we're done with our reconciliation request, we can do one of two things. If we encounter an error or decide that we need to perform more reconciliation or more work, we can push this object back on top of the queue, or we can just move on to the next one if we desire. This is controlled explicitly by the reconcile function return values. So you return a reconciliation result, and based on that result and your error, the manager will either will either move your request back on top of the queue, as I just showed, or just move on to the next one and drop it and consider your object reconciled. Testing is also scaffolded with Kubebuilder using Ginkgo and Gomega, which are two libraries that are used to create a testing DSL with a pretty rich assertion framework. The assertion framework I really enjoy working with because it has time-based assertions like eventually or consistently, so we can really test our operator in an eventually consistent way, which goes along with the general kind of how Kubernetes usually works in an eventually consistent way as well. There's also envtest, which is a package that's included that runs a Kubernetes API in memory. So you can spin up a kind of mock cluster almost instantly. It's not quite a mock cluster because there are no additional controllers running aside from your own. So um, basically, if let's say I create a deployment, nothing will happen. The deployment will be created, but no actual pods will be created because there's no deployment controller running. I have to be honest, when I first started writing these, I wasn't exactly sure why it was useful, but I realized as I started to do more with controllers, that it was really useful to be able to set the cluster in a very specific state and migrate that state throughout the course of a test to help you avoid race conditions. And then you can test and make sure that your operator performs in every possible cluster state that really matters to your operator. So I've only scratched the surface here of how we build operators. We can control object deletion with finalizers. I mentioned webhooks a couple times. There are a rich set of scaffolding plugins that come with Kubebuilder, so we can actually scaffold and create Grafana dashboards and add Prometheus metrics, custom metrics as well. Operator deployment is its own. I could do a whole talk just on that with Operator Lifecycle Manager versus Helm, raw manifests, GitOps. There are a lot of different ways to deploy operators and also events, which I find very useful as well for debugging. You can find more information on these on the Kubebuilder book, which you can Google for that. I don't have a link here, but I just want to leave with a few links. First is QuestDB, which is a demo that's running actually on the cloud. So you can kind of see this in action. It's not exactly this operator. It's meant for um, our cloud, but we're using a lot of the same concepts there. I have my blog where I write about this stuff, operators, CSI, Kubernetes internals, and also a link to the source code of this operator. So thank you very much. I really hope you enjoyed the talk and hope you learned something. I really enjoyed preparing it today, and I want to thank you for having me.
Awesome. Thanks so much, Steve. Appreciate your putting the effort into making that talk. We have a question here from Tony J. So, what is the benefit of defining CRD of snapshot schedule versus using Kubernetes native cron job?
Yeah, that's a good point. So originally, I kind of asked the same question myself. What the CRD does allow you to do is have a retention period so that you don't need to have a separate cron job to clean up your old snapshots. You can do all of that inside one controller. Additionally, I want to make sure that we don't keep failed snapshots. So let's say your snapshot failed a bunch of times in a row. Um, if you retain snapshots without looking at their phase, then you can potentially end up with only failed snapshots. And of course, you could do this in code in a script. I personally decided to do this in the operator itself. But it's a fairly lightweight controller, and you can always choose, just not to use it if you want.
Great. Oh, and then Gabriele, he said, I think this was in response to that question, but you can weigh in on it. He said, I think the top reason you decide to design a new CRD is to write how you want it, how it will be reconciled. So,
Yeah. Yeah, that's kind of, I guess, similar to what I mentioned. It just gives you more control. And there's really a trade-off again between using the components that we all know and love in Kubernetes that are, well documented and battle tested versus writing something yourself. And it's really kind of finding the line where you move from one to the other is not easy. Recently I had a situation where I was working with Prometheus operator, and I was like, I don't know like why this is happening. And I think I mentioned this like on LinkedIn or somewhere the other day. Now that you have an operator, you kind of have two problems. You have your application and then you have your operator. So that's why I really vouch for, keeping things simple, only using an operator, when you absolutely need to. So in this case, I find that the operator that I just talked about, if you're running one or two QuestDBs, our Helm chart is probably fine. But if you want to start managing 10, 50, 100 of them, all of a sudden managing those Helm deployments is going to get a little hairy.
Hmm. Yeah, that makes sense. Yeah, are there any other questions from anybody else? Feel free to add them to the chat. Uh, there's a slight delay, so I'll wait. I'll wait a few seconds before move on. But yeah, again, thank you so much for giving us this talk. I think it'll be super useful. And by the way, yeah, like Steve said, like we posted some of Steve's blog posts on the DOK website. You can find them on the in the DOK library on how to create um, a custom operator. So, oh, we have another one here. Let's see. So, yeah, sounds good. Personally, having many scripts deal with the perspectives you mentioned. Great point to have CRD with the reconciliation feature, like the programmatic pattern. Okay, so that's more of a statement there. Awesome.
Awesome.
Yeah, cool. Well, I guess if we're done with questions, we do have a quiz. So